And we have a student volunteer in the back who can pass you a post-it in case you can't reach the microphone. I did not meet the first author for the video, Jamie Allen. So in case Jamie Allen isn't here, our video chair will present the video. So our first paper compares four approaches to order picking.
Good morning, everyone. My name is An Hongguo. I'm a first-year PhD student in Carnegie Mellon. And today I'm going to present a comparison of order picking assisted by head-up display, cart-mounted display, light, and paper pick list. This work was done when I was a master's student in Georgia Tech, so you must be wondering why there are so many authors. So that's it. So each year, warehouses throughout the world distribute approximately $1 trillion in goods from nearly 1 million warehouses. And order picking is the process of collecting items from inventory and sorting them into orders for distribution. And it's one of the main activities in these warehouses, accounting for 60% of the total operational cost. So for example, in automobile companies, they spend a lot of time and money doing order picking on their assembly lines. So current practices in the industry includes pick by paper pick list and pick by light systems. In the previous work by Weaver, the use of a head-up display showed significant speed improvement as compared to a traditional text-based paper pick list, graphical paper pick list, and pick by voice system. In another work by Baumann, a qualitative study has been done to compare the four different systems in a major European automobile manufacturing plant, and also pick by cart-mounted display, as you can see on the image on the right side, was first introduced in this study. But above all, no quantitative evaluation has been performed between the different methods in a control study. So in this work, we conducted a laboratory evaluation comparing the four different systems. And our metrics were task time, accuracy, error types, subjective task load, and user preferences. Firstly, I'm going to talk about experimental setup. So there are two shelving units, A and B. Each has 4 rows and 3 columns of pick bins. So there are 24 pick bins in total. The rows are color-coded as in red, yellow, green, and blue. And the columns are symbol-coded as in square, cross, and triangle, as you can see. So in each pick bin, there are 20 to 40 pieces of one item. There is also an order card on the right side holding 3 order bins. They are also symbol-coded. Then I'm going to talk about the different methods. There are pick by paper, pick by light, pick by cart-mounted display, and pick by head-up display. First is pick by paper. So a paper pick list left image specify the location of each item, the number of items to be picked, and the sequence. The user is holding the paper and perform the tasks. As you can see, he picks up the paper pick list, look at the first subtask, picks 1 item from 1-3, 1 from 2-2, 2 from 3-3, and 1 from 4-2. Then he places those items into the order bin 1. That's how pick by paper works. Then is pick by light system. Both the pick and order bins are instrumented with LEDs. For each subtask, the LEDs will light up at the corresponding location, indicating where to pick and how many to pick. And at the same time, one of the 3 order bin LEDs will light up with a letter P, indicating where you need to place the items you picked. So as you can see, the participants picks from the shelving unit according to the LEDs, and then place, and it automatically proceeds to the next subtask. We are using vis-a-vis method in this study to stimulate the use of actual proximity sensors. Then is pick by cart-mounted display. A graphical display is used to represent the pick tasks. On the left side, this colored grid is used to display the pick bins. And on the right side, another grid represents the order bins. So here is how pick-by-cart mounted display works. The information is presented on a 13.3-inch MacBook Pro with Retina display mounted on the cart. The fourth method is pick-by-head-up display. So a head-up display is used and the information is overlaid on the user's visual field as they walk around. And as you can see, the user interface is same as the pick-by-cart mounted display. So here is how pick-by-head-up display works. The information is presented on a micro-optical SB3 connected to a laptop and in the backpack worn by the user. So then we did a user study with the experimental setup. The study environment is set up as the image. We recorded the entire study procedure with a front and back video camera. The man in green is our participant. The man in black are our experimenters. One experimenter is in charge of proceeding the tasks to stimulate the proximity sensors. The second experimenter is in charge of the order bins. So after each task, the experimenter 2 photographs the order bins and reset the experimental setup. So we evaluated the system with 8 participants, 3 female, all students with an age range of 22 to 27. All are right hand and 4 are left eye dominant and 4 are right eye dominant for head-up display. All 8 of them are novices at all 4 different methods. So they first go through training. They first complete the practice sessions for each method with 5 tasks for each training session. And then they do the testing, which they do 10 different tasks for each session. So after each method, so one of the training or testing sessions, they fill out NASA Task Load Index survey to measure the subjective task load. And after the whole study, they rank the systems. So based on the data we gathered according to our matrix, here are the results. So we are only counting the last 8 tasks of the test session to avoid learning effect. From the learning curve, we can see it is generally consistent and no learning effects is shown. So our hypothesis was that head-up display is the best, which means has fewer errors, faster performance, lower cognitive load, and higher preferences. And for all the t-tests we run, we use a significance level of 0.05. So first is average test time. For manufacturers and suppliers, they care a lot about the speed of doing order picking, because that means how many people they need to hire to do that. So we can see head-up display has a 38% improvement over paper and is significantly faster than light and paper. So the star means head-up display has a significant improvement over that method. So they're also showing up in the later slides. So the manufacturers and suppliers care about the speed, but they care more about the errors, because the errors are stopping their assembly lines or making their customers angry. So the result is head-up display has an 80% improvement over paper and has even more on light. So then if we compare the 4 different methods based on their error types, you can see in the graph, we place different error types on the stack bar chart based on their negative impact on the assembly line. So on the right side of the black separator line, there's more number and additional part error, which means you picked more than you should. Those are not severe enough to stop assembly line, because after you assemble, those will be left out and you can put them back. But on the left side of this black separator line, they are sufficiently severe to stop assembly line. So if we only look at those severe errors, here's what we get. And then let's look at the different types of errors. First is wrong order bin errors. So wrong order bin errors means after you pick from the shell unit, you put into the wrong order bin. Instead of 1, you put into 2. We can see it happen a lot with pick by paper. This is because it requires a lot of very high memory load. And when you finish picking from the shelf, you already forgot where to put them. Then is substitution errors. It means you picked from the wrong pick bins. And so in substitution errors, there are substitution wrong shelf, which means you need to pick from A, but you pick from B, or the other way. And also wrong column and wrong row. So especially for the wrong shelf errors, it happens only on card-mounted display. This is happening when the participants finish a task in standing in front of shelving unit B, and then they wait for the next task to come out, and then you show up, and he should go back to shelving unit A to do the picking, but he directly continues to pick from B. But including other kinds of substitution errors, we can see it happens a lot for both card-mounted display and paper. So for paper, there's not a natural mapping between where you need to pick and what you need to do, what you see and what you need to do. And for card-mounted display, you need to look back and forth with the display, and the user sometimes, when they look at the display, they use peripheral vision to do the picking, which causes problem. For a head-up display, we see there are no substitution errors happening. This is because for head-up display, the participants get a better view of the shelving unit because they are always facing it when doing the picking. And for light, we can see there are also no substitution and wrong order bin errors. This is because it's also very natural mapping for where to pick and where to put. And the knowledge is in the world on LEDs. So the users don't need to think about it. However, they still need to see them. We can see a lot of missing part errors happen. That means they simply skip them. They didn't see that and didn't pick it. And if we look at where the errors are happening on the shelf, we can see a lot of them are on the edges. All of them are on the edges. That's because when they pick, they can't have a whole view of the shelf. They need to step back to see the whole shelving unit and step forward to pick. And considering all the critical errors, we can see card-mounted display actually has 3 times the number of errors than head-up display, even though there are no significant difference shown in the data. Then for overall task load, we measure this using the NASA task load index surveys. The head-up display showed significant improvement compared with light and paper. And in user preferences, we asked them to rank 1 to 4 of the different 4 methods, and then we calculate the median of those rankings. And we can see overall more people rank head-up display as their #1 choice. So we can see head-up display offers superior performance to pick by light and pick by paper. And unexpectedly, post-hoc analysis also showed that card-mounted display showed similar performance to head-up display. And for cost, light is much more expensive than the others, which costs over €1,000 per meter to upgrade the production line in only hardware. And however, for a head-up display and card-mounted display, it's much cheaper. Then more specifically for pick by paper, the users are holding the task with one hand, so they only have one free hand to do the picking. That greatly reduces their speed. And also due to the number of items they can hold in one hand, they sometimes need to split one subtask into multiple parts. So that also reduces the speed. And the probable reason for why there are so many errors for pick by paper is that it requires a very heavy memory load, and there is no natural mapping. So pick by light is much faster than pick by paper, in part because the users can employ both hands to do the picking. However, with pick by light, the users need to visually scan the shelving unit from top left to bottom right, and that takes time. And also they need to step back frequently to see the whole shelving unit because they can't keep the complete context in their head. So pick by card-mounted display is cheap and fast, and they can use both hands to do the picking. However, the user may need to turn their heads towards the head of the display and the shelving unit to do the picking. And if their focus is mainly on the display, it might cause a problem when they use peripheral vision. So pick by head-up display is fast, mainly because they can use both hands and the display is always available. they don't need to step back and forward as with pick by light, and they do not need to turn their heads every now and then as with pick by card-mounted display. So although the participants in the study does not necessarily have any previous experience with head-up displays, pick by HUD is not harder to learn than any other methods according to the user's rankings. And in fact, pick by HUD was even significantly easier to learn than pick by paper. And for our current testing systems, participants need to wear a backpack with a wearable computer in it. And however, according to the users, head-up display was no less comfortable than light and even more comfortable than paper. Previous work has also shown that head-up display in real-world warehouses can be used by the workers continuously over weeks without any difficulty. This will also be improved by the more advanced head-up displays coming out like Google Glass. So we have shown that head-up display could have significant improvement in both time and error than the current industrial practices, and could have significant cost savings for manufacturers and suppliers. However, we are using an optimized lab setting and dense peaking environment. Whether that holds true in the actual warehouse, we would need to do some additional testing in actual manufacturing environment in order to know that. And overall, we didn't see any significant difference between HUD and CMD. However, CMD exhibits 3 times the number of critical errors than HUD. In the future, we would also like to evaluate more head-up display systems to see whether we can find further improvements. We are conducting another study comparing card-mounted display with 3 different kinds of head-up displays, including the existing one we use for SV3, and also the 2i head-up display Epson Moverio and Google Glass. So that's all I got. Thank you.
Thank you. I thought the presentation was excellent. I appreciate it. It was really clear. So I'm David McGee from ADAPTS, and my question is, you chose to use a different visual presentation for the paper display, and I'm wondering why that is and how you can be sure that it didn't have a huge impact on your results.
You mean why I didn't use graphical on the paper?
Precisely.
Oh yeah, so because the paper presentation in our study is like what the warehouses are using right now. That's the thing they do now. Yeah.
Okay, so how can you be sure that didn't have a really huge impact on the results comparing paper to HMD and others?
So, so here, based on a previous study, they showed head-up display shows significant improvement over even the graphical paper pick list.
Questions? One quick question about the HUD case. You're using the SV3, which has a tiny exit pupil. So maybe this will come out when you compare. You know, you won't. When you do the next study, but does Amy Ross mentioned some issues with the head-mount display users having to look through it, mostly related to eyebox and positioning. Do you anticipate similar problems that are optics related that could be improved?
Yeah, so we are thinking of comparing the different head-up display systems, and they will not only show whether it works best for the water picking, they'll also hopefully show the different differences between the head-up display systems. For example, let's see, there's as you can see in this one, the different displays we can also show like the positions of the display and the transparency and weight and whether it's 1 eye or 2 eye. So hopefully in the later studies we can show that. Yeah.
Are those axes the center of mass or?
Yeah.
Okay.
Hi, Greg Nelson, University of Washington. in terms of the users making an error in the task, so if they try to slow down, they probably have fewer errors. And then also, when you make an error, sometimes you realize afterwards, oh yeah, I put that in the wrong place.
Yeah.
So could you talk a little bit about like how you observed that in the user study, or if that was just something where it's like, go as fast as you can, don't worry about making mistakes. I wonder how prompting people would get them to make their own trade-offs in that kind of area.
So in the user study, we ask them to do as fast and as accurate as they can, but like we are not asking them to correct their errors. Yeah. So, and if we consider the situation that correcting those errors have bad consequences for that. Yeah. So you also must be wondering why there are so many errors in light than paper, because that's believed to be the best practice in the industry. That's because in many pick by light systems, they also have the laser scanner on top. So it knows whether or not you picked from the right place or not. But that is always false trigger in the real scenario, because sometimes you are picking from the bottom pick bin, then your head first get into the laser scanner, then you need to press the button to say I didn't pick from this one, and press the other button to say I did pick from this one, and it's very irritating. And also you can imagine it takes a lot of time to correct those errors. So even though the errors may reduce, the time will hugely increase. And actually, when we are looking at the different error types, you see in the HUD and the light, those are all the errors are related to like more or less. Yeah, so we can also easily use a scale feedback system to correct the errors instead of using the laser scanner, and it's also much cheaper.
Questions? So for pick by light, I heard there's some error checking mechanisms in industry. So for any of the four methods you've compared, are these the optimal implementations?
Oh yeah, so for pick by paper, that's what they are using in the industry. And pick by light, I just mentioned about they sometimes use that, but it increased the time a lot to decrease the errors. And but they sometimes they also use like brighter LEDs and yeah, they need you to confirm after you pick from each place, and they also maybe have like some audio feedback. But like generally from our user study, so the setup with light is trying to be as close as the actual industry environment, and also trying to be similar to our card-mounted display and head-up display system, the display. Yeah.
Any other questions? Let's thank our speaker.
Thank you.